Hello everyone, this video is brought to you by the Atılım University OpenCourseWare project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and the video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 10. A bicycle well has an initial angular speed of 1.5 radians per second at time t equals 0. The questions are: A. If its angular acceleration is constant and equal to 0.3 radians per second squared, what is its angular speed at time t equals 2.5 seconds? B. Through what angle has the well turned between t equals 0 to t equals 2.5 seconds? At t equals 2.5 seconds, the well starts to slow down with a new angular acceleration of magnitude 0.15 radians per second squared. C. How many revolutions does the well make until it stops? D. Find the time required for the well to stop. First, we write the given quantities in SI units as follows. Where omega 0 is the initial angular speed, alpha 1 is the first angular acceleration, and t1 is the time when the well starts to slow down, alpha 2 equals minus 0.15 radians per second squared, and final angular speed, say omega 2 equals 0 since it stops. In part A, in order to find the angular speed at time t equals 2.5 seconds, since we have a constant angular acceleration with magnitude 0.2 radians per second squared, we use this formula, where omega 0 is the initial angular speed and omega 1 is the angular speed at t equals 2.5 seconds. Alpha 1 is the initial angular acceleration and t1 equals 2.5 seconds. Then put the numerical values into this equation as 1.5 radians per second plus 0.3 radians per second squared times 2.5 seconds. If you calculate, you obtain 2.25 radians per second. In part B, to find the angle between t equals 0 and t equals 2.5 seconds, we use this formula. With this formula, the expression for the delta theta 1 is found to be omega 1 squared minus omega 0 squared over 2 times alpha 1. If we put the corresponding numerical values into this equation, you get approximately 4.69 radians. In part C, again we use this formula to find the revolutions the well make until it stops. Here omega 2 is the final velocity, which is 0. Omega 1 is the angular speed that we have found in part B. Alpha 2 is the negative angular acceleration for the well to start to slow down. And delta theta 2 is the number of revolutions the well make until it stops. From this formula, we can get an expression for delta theta 2 as omega 2 squared minus omega 1 squared over 2 times alpha 2. Now, put the numerical values into this equation as 0 squared minus 2.25 radians per second squared divided by 2 times minus 0.15 radians per second squared. And the result is 16.25 2.875 radians. However, in order to find the number of revolutions, we have to convert radians into revolutions as follows: 16.875 radians times 1 revolution over 2 pi radians, and we get approximately 2.69 revolutions. In part D, we find the time required for the valve to stop using this formula. Now, T2 is obtained as omega 2 minus omega 1 over alpha 2. Put the numerical values into this equation to get 0 minus 2.25 radians per second divided by minus 0.15 radians per second squared. Finally, the time required for the valve to stop is found to be 15 seconds. Okay, this is the end of the solution of this problem. Thank you for your attention and see you in the next video.